Okay, so I will start presenting the work that I have achieved during the last 3 years in my PhD thesis, entitled Turn-Taking Enhancement in Spoken Dialogue Systems with Reinforcement Learning. So this is a collaboration between Orange Labs and the University of Avignon. And the problem that I'm dealing with is related to human-machine vocal interaction, since I believe that this can lead to more natural user interfaces, which can really make the difference in some situations, especially when the user's hands and eyes are already busy, for example, while driving, while cooking. But what we see currently is that such systems are not as widely used as they could be, unfortunately. And this can be due to several reasons. For example, bad dialogue management, which means bad content delivery and understanding, but also to bad turn-taking management. So in order to give you an intuition of what is a bad turn-taking management situation, I will share with you the following video.
How are you?
I am doing
Fine?
well. What
Hang in there.
can I do
Well, I was hoping you could run a play.
for you
Well, I was hoping you
today?
Well, I was hoping you could run a play for us. We are in a really big hurry.
What's the plate
29 T
number?
29 THD03.
2 9 T
HD03.
H
D03.
D
03.
0.
3.
Hey, Flash, want to hear a joke?
No!
Okay, so I guess that you get the point. So this kind of frustration is something that's very often encountered, unfortunately, when users try to interact with machines. And this is what I dealt with in my thesis. So how can we enhance dialogue systems' turn-taking capabilities, and most importantly, how can we make them learn optimal turn-taking strategies directly from data? This is the approach that I have adopted throughout the thesis. First, I asked myself, what is turn-taking, which led to the establishment of a new turn-taking phenomena taxonomy. Then the question was how to replicate such turn-taking behaviors in a dialogue system. So this leads us to the literature about incremental dialogue systems. And here I have formalized my own approach for that. Once we have an incremental dialogue systems, what turn-taking behaviors do we want to implement in it, given the situation at hand, and how? In order to perform a first evaluation, I designed a simulated environment for incremental dialogue, which was also very useful to generate a massive amount of data, which has been fed to a new reinforcement learning algorithm for turn-taking optimization. And finally, the results have been validated in a live study with real users. So this is how this presentation is going to be organized. First, I will provide a few definitions and elements from the state of the art. Then I will present my contributions before concluding and discussing a few perspectives. So starting with spoken dialogue systems and incremental processing. First, what is a spoken dialogue system? It can be defined as a system that interacts vocally with users in natural language in several dialogue turns. So this is to be distinguished from simple question and answering. And this is how we traditionally break a dialogue system into 5 parts. So the audio signal coming from the user is processed by the automatic speech recognition module, which transforms it into text. This text is then fed to the NLU, which outputs concepts that are ready to be consumed by the dialogue manager, which in turn outputs a new dialogue act. And through the NLG and the TTS, it is transformed into an audio signal which is hopefully understandable by the user. In the traditional setup, in traditional dialogue systems, the user's utterances are processed by the system only once finished. So if you are used to a personal assistant in your smartphone, for example, what you might have noticed is that you have to finish your sentence, the system detects a silence, and then it decides to start processing your utterance. This is obviously not how human beings communicate. So you're not waiting for me to finish my sentences before understanding them. You are understanding them and processing them on the fly, and this is what we are trying to replicate in incremental dialogue systems. So we process the user's information as new information comes in, and this makes them able to perform interesting behaviors like interruptions, feedback, and back channel, and they can also be interrupted by the user. So there are more advantages than traditional systems in the sense that they are more reactive, they are more engaging and human-like, and as we will see in this thesis, they are also able to repair errors more quickly. However, they also come with a few challenges since they must be able to quickly process the user's utterance, to handle partial and unfinished utterances, and also to handle revisions, in the sense that as new information comes in, it is possible that the whole meaning of the user's utterance change. So how is that related to turn-taking? First, what is turn-taking? It can be defined as the way the dialogue participants take and release the floor. A more general definition, proposed by Sachs in his paper in 1974, is an economy where turns are valued, sought, or avoided. And incremental dialogue systems can be viewed as a way to relax this rigid constraint imposed by traditional dialogue systems. As a consequence, it makes them able to perform a richer and more interesting set of turn-taking behaviors. So in the field of spoken dialogue systems, machine learning has been widely used because of this idea of aiming for the best, for the optimal strategy, but also because they make these strategies grounded and based on real dialogue data. And in the field of dialogue management, precisely, reinforcement learning is particularly adapted for several reasons, and mainly because it makes it able to learn from delayed rewards. So we can only say that a dialogue is good or bad generally at the end of the dialogue. Reinforcement learning has been studied initially in the field of biology, since we all know that living organisms, animals or humans, learn by seeking rewards and avoid punishment. And this has been shown in several previous studies. And what's interesting for us is that it can be cast as a mathematical framework when we have an agent that's evolving in an environment. So at time t, the agent is at state st, then it makes action at, and as a consequence, the environment changes the agent's state to st plus 1 and provides a new reward, rt plus 1. Generally, these agents are cast as a Markov decision process, which is a quintuple. So we have the state space, which is the set of states where the agent can be, the action space, which is the set of actions that it can take, the transition model that gives us the probability of being at a certain state given the previous state and the previous action, the reward model, which gives us the distribution of the rewards given the previous state and the previous action, and finally this discount factor gamma here between 0 and 1, which I will explain in the next slide. So the objective of reinforcement learning is to find a policy, which is a mapping between states and action. So if I am at state S, what is the best action that I should take? And this policy should maximize the expected discounted reward, which is given by this equation here. And you might have noticed that the farther in time, the farther the reward is in time, the less importance it is given because of this gamma factor here. Remember, it's between 0 and 1. And most algorithms actually they denote this expected discounted return as a function of the current state and the current action, and this function is called the Q function. So this is the leading machine learning framework for in the field of dialogue management. It has first been proposed about two 2 decades ago by Levin. And since then, we've noticed several improvements, important improvements, like the ones listed here. And as far as turn taking is concerned, there are also a few studies that try to apply reinforcement learning to the problem, like this one where they use prosody only, the second one where they used hierarchical reinforcement learning to simultaneously learn turn taking along with the dialogue management, and also this interesting study where reinforcement learning, inverse reinforcement learning, has been used to directly imitate humans' turn-taking behaviors. And in this thesis, I will propose a new reinforcement learning-based turn-taking strategy that is going to directly learn from the global dialogue quality. All right, so moving to my contributions and starting with the turn-taking phenomena taxonomy. So when we talk about turn-taking, a question arises, which is what phenomena characterize turn-taking in a human conversation, and how can we identify and classify these phenomena given the differences and the similarities between them? And based on that, can we draw a general picture of these phenomena, and can we come up with general categories of them? And finally, and that's what interests us most here, is what phenomena are really worth implementing in an incremental dialogue system given the situation at hand. So in each floor transition, we can distinguish between the two dialogue participants. So we have the floor holder, which is initially having the floor, and the floor taker, which takes it afterwards. And since this is a study that is more focused on the semantics and on the content of each of the participants' dialogue act, I have chosen to perform this study based on these two dimensions here. So the first one is the quantity of information that the holder has already injected in the dialogue from the taker's perspective. And the second one is the quantity of information that the taker tries to inject by taking the floor. So this is how the taxonomy looks like. Each row represents a different level in the first dimension, and each column represents a different one in the second dimension. So starting off with the last row, which is actually the easiest to understand, H complete means that the holder actually finished his or her sentence and stopped. So just a side note here, to make the explanation more fluid, I'm going to call the holder Hector, and the taker is going to be called Tanya. So suppose here that Hector said the metro traffic is disrupted, stop. Tanya can actually choose to rekindle this sentence because she thinks that it's incomplete. There's still some missing information. So she can do that either implicitly by frowning, for example, in a row manner, by saying and, or in a more interpreted manner by saying, oh, that's for sure, since 2 hours, and is there anything I can help you with? On the other hand, she can also choose to just provide a new utterance, a new sentence that is aimed to move the dialogue forward by saying, for example, yes, you can take the bus instead, it's upstairs. And this is the most common case that we think about when talking about dialogue. So moving to the next row, H sufficient means that the taker thinks that enough information has been provided by the holder, even though the latter has not really finished speaking. So the first case is when the holder actually provides an enumeration of several options, and the taker just barges in at right after the option that interests him or her the most. So let's say, for example, Hector says we can meet on Monday, Friday afternoon. Then Tanya can intervene to select the Friday afternoon option, either implicitly by performing a head nod, or in a row manner by saying, okay, great, or in a more interpreted manner. Also, Tanya can just provide a new information to move the dialogue forward without pointing, without any reference to the holders, to Hector's utterance. So, like for example here, what is the digicode? I have been. And Tanya just barged in by providing the information requested by Hector. Then we have the H incomplete level, meaning that Hector has not really finished his sentence, But Tanya decides to intervene anyway. This can be done to make some kind of back channel, like a head nod or saying aha, or performing feedback. So just repeating what has just been said or in a more interpreted manner. So these three phenomena are not here to really barge in to interrupt the user, but just to report that Tanya has actually understood what has been said so far, encouraging him to continue. And finally, we have the real barge in, which happens sometimes, especially if Tanya thinks that she has a more urgent or important thing to say. Like here, for example, when she realized that somebody has just stolen her wallet. Moving to the H incoherence level now. So what it means is that Hector has not finished his sentence, yet Tanya thinks that it's already problematic. There's something that's incoherent or that's that's impossible in Hector's sentence. So, for example, here, suppose that he's saying, "I would like to book a room for tonight, and I want a parking. I'm gonna have a pet, etc., etc." If the hotel is fully booked, then it makes sense to interrupt him right away. And this can be done in an implicit, in a row, or in an interpreted manner, or again, by providing some useful information to move the dialogue forward. Like in this example here, she responds by saying, "I suggest that you check the hotel downstairs. We are fully booked, sorry." If Tanya does not understand what has been said at all by Hector, we're going to talk about H-fail phenomena. So it can be due to noise or due to using words or expressions that she does not understand. And again, she can report that in an implicit row or interpreted manner, or she can provide some information, some new information, like here, "Well, I can't hear you, but please don't be late for the event. Sorry. And finally, we have the H-non level, and in this case, nothing has been said so far. So we have a holder, but he's only a holder by convention. And Tanya can actually take the floor. So these are actually dialogue initialization phenomena. So she can take the floor in an implicit manner by clearing her throat or by waving. She can just say, "May I speak?" That's the raw fashion of starting the dialogue, or in a more interpreted manner. Or she can just dive into the subject right away by providing a new utterance with a new information, which is relevant to the dialogue. Now that I have described how this taxonomy works, what we can see is that we can actually draw or depict several categories of similar phenomena. And this is an example of one possible categorization. So we have the first row with all the dialogue initialization phenomena. We have the negative and the positive feedback. We have the reference phenomena. And here in green, we have all the phenomena where we have a new sentence provided by the taker, which contains a new information which is relevant to the dialogue. Alright, so as I said at the beginning of this presentation, traditional dialogue systems are very limited in terms of turn-taking capabilities. So in order to replicate a more interesting set of turn-taking behaviors, of turn-taking phenomena that we just covered, we need an incremental dialogue system. So when we look at the literature of incremental dialogue systems, we can actually group them into two categories. And the first one being what I call the modular paradigm. So in this setup, each module of the dialogue chain is going to be transformed into its incremental version, or at least some of these modules. Whereas in the second category, what I call the multi-layer paradigm, we're going to keep the dialogue chain as it is actually, and we are just going to add a new layer which will handle turn-taking. So we have a clear separation between the dialogue management and the turn-taking management part. And this is what we are actually going to use here. So a classical dialogue system can actually be broken into a client and a service. So the client contains the ASR and the TTS, and the service contains the dialogue manager. The NLU and the NLG can be both sides, depending on the situation at hand. And we just have to make sure that the ASR is able to provide partial results and the TTS is able to be interrupted by the user. And in order to introduce incremental behaviors, incrementality, what we do is we add this new module between the two, which we call the scheduler, which will, as we will going to see, it will handle turn-taking decisions. So how does that work? Actually, in the traditional setup, we have a clear separation between user and system turns, and the user turns is clearly defined by a condition, which I call here the end of turn condition, and generally it's a silence threshold. When switching to incremental dialog systems, what we are going to need are microturns, which are actually smaller subturns. And we are going to have an end of microturn condition which happens more frequently, like for example every 500 milliseconds. So to explain how this architecture works, suppose that the user is saying, has just said, I want to book a hotel room, for example. Then at each new microturn, the client is going to send the whole partial utterance that has been understood so far. So for example, at the first microturn, it can send I, then I want, then I want to, then I want to book, etc., etc. So we have growing partial utterances that are going to be sent to the scheduler, and at each time the scheduler receives some input, it will request the service, it will ask the service for a corresponding response. And then, depending on this response and some other context feature, the scheduler has to make a decision either to retrieve this service's response to the client or not. And this is a key point here because this is how it will decide to take the floor or not. And this actually raises a new problem residing in the fact that even though a partial utterance is meant to be dismissed by the scheduler, the service's context might be altered, and this is not something that we want to do. So at each time that we decide to discard a partial utterance, the service is the dialog state is going to be cancelled or rollbacked. So it's meaning that we are going to revert back to the state it was in before this partial utterance. And how do we manage this mechanism here? We actually maintain two dialog contexts, the permanent context and the temporary context. And we say that we commit. So committing to a partial utterance means that we decide to actually take the floor as a result of this partial utterance. So when we say that we commit, when we copy the temporary context into the permanent context, and we roll back or cancel when we perform the opposite operation. So now we are left with this new setup here, where we have each turn is divided into smaller microturns, and we have two cases where where we switch from the user to the system to the system's turn. It can be either as before after an end of turn condition, or due to a spontaneous scheduler's decision. On the other hand, from the user side, we have the same thing happening. So either the user waits for the TTS to stop, or he or she decides to barge in. So in order to understand how this architecture actually fits in the panorama of existing incremental dialog systems, I have proposed this classification here in 4 categories of dialog systems given their level of incrementality. So the first one is the first category contains non-incremental dialog systems. Then we have the second category, which I call auxiliary incremental. So we have a few non-incremental dialog systems that will actually offer some isolated incremental functionalities. And then we have the simulated incremental, and this is where our architecture fits in. So because we managed to actually simulate incremental dialogue while keeping a non-incremental dialogue management setup. And finally, we have the fully incremental setup, which I described a few slides ago as being as coming from the modular paradigm. And if we analyze the features, the incrementality features that all these systems actually offer, what we realize is that the simulated incremental category actually can replicate all the features that are offered by the fully incremental setup, but we miss in some cases the optimal processing cost, especially if there is an extensive and time-consuming treatment involved behind the dialogue manager. And this is due to the fact that we are actually asking the service to process the whole partial utterance from the beginning at each new microturn. So just to recap and to give the pros and cons of this approach here, it is very interesting because it can transform a traditional dialogue system into an incremental one without having to start from scratch. It also clearly separates the turn-taking management part from the traditional dialogue management part, but in some cases, if we have some extensive treatment involved, it might be better to go for the fully incremental setup. Alright, so now that we have an incremental dialogue systems architecture, the question is, what are the turn-taking phenomena that we want to implement in it? But before tackling that question, let's go back and talk a little bit about how traditional dialogue systems parse the user's utterances. What they do is actually look for different information slots, and this is what we refer to as slot filling. So, for example, if the user says, "I would like to buy the book Dracula by Bram Stoker," you see here that the system can fill, depending on the information which is relevant to it. It might fill these four slots here: the action, the object, the title, and the writer. Well, of course, we have other ways to parse the user's utterance, but this is the most simple and the most widely used manner. And there are several dialogue management strategies in order to gather these slots. Just a quick note, the terms that I will introduce here are widely used, and their definition might vary from author to author, but here I will define them as such, and I will stick to those definitions. So when I talk about the system initiative strategy, I mean that the system asks the user to provide all the slots one by one. So after asking for a slot, if there is a problem, the system will actually ask the user again until it manages to retrieve a valid information, and then it can move to the next slot. Then we have the user initiative strategy, which means that the system is going to ask the user to provide all the slots at once, and if there is a problem, the user is going to be asked to repeat his or her request again. And finally, the mixed initiative strategy starts like just like the user initiative setup. And if there is a problem, if there are missing slots, the system is going to ask the user to provide them one by one, which means switching to the system initiative strategy. So the scheduler here is able to perform three types of actions: the wait action, which means doing nothing, just waiting for the next microturn; the speak action, which means to take the floor and hence committing to the last partial utterance; and the repeat action, meaning that the system is going to repeat a portion of the last user's partial utterance. So the incremental strategies that we have chosen for implementation here, since we believe that these are the ones that are the most likely to improve the dialogue in a task-oriented setup, The first one is fail row, so meaning that when the user is speaking and the system has not understood nothing so far, it can just interrupt him or her and ask for a repeat or for a reformulation. The incoherence interrupt phenomenon means that the user has actually provided some information, but the system detects that there is a problem with that, so it barges in right away. In the feedback row, there is no barging involved, but the system decides to repeat a portion of the user's utterance because it doubts that it has been properly understood. And finally, the barging rest phenomenon has been implemented from both sides, both the system and the user side, meaning that if the system thinks that there is enough information to provide an answer, it will do that right away without waiting for the user to finish his or her sentence. And also, as the user gets familiar with the system, she might want to actually interrupt the system before the end of its dialogue acts because she guesses what she guesses the rest of its utterances more easily. So now we have all the necessary elements in order to start implementing dialogue actually and interacting with our incremental dialogue system. But since we should keep in mind that we are going to use that in order to use machine learning and reinforcement learning, what we decided to do first is to implement a simulated incremental dialogue environment in order to be able to generate a massive amount of data. So this is what my simulated environment looks like. So we have the user simulator with the several components that I will describe in a few slides, and we have the ASR output simulator, and these two, the combination of the two, can interact with any incremental dialogue system. In order to really implement dialogues that will run in the simulator, we first need a domain for practical reasons, obviously. So here I have chosen a personal agenda management domain where the user can add, modify, or delete events in his or her agenda. So there are 4 slots involved in this task. So the action type, the event name, the date, and the time window, with one constraint is that there are no overlaps allowed between events. So it's impossible for the user to book an event or to schedule an event or 2 events with overlapping time windows. So I start with the intent manager, which is basically an inverse dialogue manager, which is initially provided with a list of pre-scheduled events prior to the dialogue and a list of events that it should add to the agenda during the dialogue. And each event is associated with a priority value, and the goal is to make the events that are the more priority fit in the agenda. So here's a dialogue example with the mixed initiative strategy. So here the user asks for all the slots, but unfortunately the date is missing, so it asks for it again until it gets it, and then it asks for a confirmation which hopefully the user will say yes to. The NLG is very straightforward. Here I distinguish between the NLG and the verbosity manager, but these 2 elements can actually both grouped into the NLG block. But here I just wanted to actually distinguish between 2 types of behaviors. So when I talk about the NLG, it's the module that outputs very simple, straightforward utterances like this one in this example. And the verbosity manager is here to actually make things more realistic by, for example, adding some of domain utterances, adding prefixes and suffixes like I would like to, please, and sometimes repeating the same utterance twice, especially when there is a misunderstanding. Now moving to ASR, and Before that, we need to understand a very important problem when it comes to incremental processing. It's the problem of ASR stability or instability. So just to give you a hint of what does that actually refer to, suppose that the user says Czech Republic. If the ASR processes that incrementally, it might first output Czech, then check the pub, then Czech Republic. So as you might have noticed here in the third result, it's completely different from the first one. The world Czech has been completely revised. So it's important actually that the scheduler here waits for the sentence to or just gives it little time to stabilize before taking action. So here we makes it actually wait for a little time interval, which we call the stability margin. So how do we simulate ASR instability? Suppose that the user says, I want to add the event birthday party on January, and then in the next microturn we understand 6th. So what we do here is that we have an old nbest and we generate a new nbest only for the new word. Between brackets you have the scores, and what we do is that we multiply the scores of the old nbest with the hypothesis of the new one, and we select the hypothesis with the best scores, which gives us our new combined nbest. But if you look at the fourth hypothesis here, what you see is that a new concept has appeared in that hypothesis, which is January 6th. So it's an interesting concept for us, and it makes it likely that this is the real hypothesis actually. So what we do here is that we are going to boost its score given this formula here, and this gives us a new nbest, which actually here the boosting effect was enough to make the fourth hypothesis go to the top. So actually we do this just because we do not have a language model for our ASR. So this is what real ASRs do. They use a language model for that, but here we just use the NLU instead. So our NLU is just a simple keyword spotting algorithm, and the patience manager simulates the fact that users might hang up before the end of the dialogue, especially if the dialogue gets too tedious for them. So in simulation we don't have a timing concept, so what we do is that we make the hypothesis that both the user and the system they speak with a speech rate of 200 words per minute, and we also add an assumption concerning silences between turns. So now we can start implementing the dialogue strategies in our simulated environment. So recall that we have 3 slot-filling strategies: the system, user, and mixed initiative, and we have 5 turn-taking phenomena that have been chosen. We combine them with the user initiative and the mixed initiative strategies, since in the system initiative the dialogue acts are actually too short, so it's not really interesting to process them incrementally. And for the simulation we use the word error rate as our proxy for measuring noise. We made it vary between 0 and 30%. Also we had 1,000 runs for each strategy and word error combination. So we used the task completion ratio as a measure for the dialogue quality, and what you might have noticed here is that for low noise situations, the user initiative strategy is much better than the system initiative one, but as noise grows, it's actually the opposite case. But when using the mixed initiative strategy, it actually brings up the best of both worlds. So this is not a new result here. This is something that has already been proven, but it just confirms the well functioning of our simulator. But what's really interesting is that by applying incrementality, by adding incrementality to the user initiative strategy, what we notice is that it's even much better. It's even better than the mixed initiative strategy, So what it shows here is that actually incrementality can be viewed as a kind of mixed initiative, not from the dialogue management part, but in the from the turn-taking perspective, since both the user and the system can actually take the initiative to take and release the floor. And finally, if we add incrementality to the mixed initiative strategy, we get the best performances. In this slide here, I have split the turn-taking strategy into its different components, the different phenomena. And this is a very interesting approach, since it lets us know what are the phenomena that are really improving the dialogue given the situation, and which ones are not really. And this actually justifies this approach when we use both the turn-taking phenomena taxonomy and the scheduler approach, and it's very easy in the scheduler and to enable and to disable any phenomenon that we want. Alright, so everything that we have accomplished so far is based on rules, on handcrafted rules. So we have no guarantee that the implemented behaviors are optimal. And the challenge in this thesis is to show that we actually can learn turn-taking behaviors directly from experience, from data, using machine learning. And we show that the reinforcement learning is especially adapted to this task. So our scheduler can perform two kinds of two actions, wait and speak. And the rewards are only computed at the end of each independent episode. So this is one of the main reasons why we have chosen reinforcement learning instead of other machine learning frameworks. And this reward is computed as a linear combination between the duration and the task completion. So we want high task completion and low duration. So how do we compute our state? It's actually based on 5 features. System request, which is the system prompt. Here, what can I do for you? It's an open question. Then recall that the service is asked for a response at each new microturn. So this is our second feature. Here the user has only said I, so the second feature is a misunderstanding. Then we count the number of words that have been uttered by the user since the last change of one of the two first features, starting at 0. Then we take the normalized score, so the ASR score. It's normalized because we take the geometrical mean in order not to penalize long sentences, and we also take the time into account. So just to show you the evolution, so here the user says I would. You see that the 3 last features are moving, and the second feature will only move when there is a new concept here. Alright, so the objective is to use a linear model based on a state vector. So our Q function will be a linear combination of these features here. So the deltas are the different possible combinations of the first 2 features. Then we use RBFs to represent the third feature. The fourth feature is also represented using radial basis functions, and the time is taken as it is because it is monotonous, because the Q function is actually monotonous as a function of time. So we use Q learning, which happened to be a very slow learner, so we preferred the fitted Q value iteration. It's a batch algorithm, but we used it in an online fashion since we update our model every 500 episodes. It is worth mentioning that we faced a new problem, which is due to the fact that in the optimal policy, the action weight is taken more often, much more often than the speak action. So if we make the decision to speak very often, we might actually hurt the exploration process. So how did we do that? How did we deal with that? We actually biased the exploration by taking the wait action 90% of the time and the speak action 10% of the time. This, of course, during the exploration phase. So this is our learning curve. Between 0 and 500, we performed only pure exploitation, so totally random. Totally random but biased. And between 500 and 2500, it's a mix between exploration and exploitation. So it's an epsilon greedy with epsilon equals 10%. And between 2500 and 3000, we performed pure exploitation. So that's why we see this jump here. And we see that we have that this new strategy actually outperforms both the non-incremental and the incremental baseline. And this slide is just to show you that the reinforcement learning based strategy is actually more robust to noise compared to the other two baselines. So now that we have all our strategies in place, instead of evaluating them in a simulated environment, we evaluate them with real users in a live experiment. To do that, I designed a new prototype, which was part of the VoiceHawk project at Orange Labs, where the users were interacting with the smart home. So it's a slot filling task, quite similar to the agenda task with 4 slots, the action type, so either to schedule, modify, or delete a domestic task, the name of the domestic task, the date, and the time window. With one constraint is that there are a few domestic tasks that cannot be scheduled simultaneously, like heating and air conditioning, for example. So this is what the user interface looked like. So the users had to read a text with a synthetic table here. Then they start by clicking on this green button here, and either they naturally end the dialogue, or if it gets too tedious for them, they click on this hang up red button here. So here I have 2 examples that I'm going to share with you, 2 dialogue examples.
Bonjour. Grâce à ce service, vous pourrez interagir avec votre maison en vous exprimant naturellement. Je vous écoute.
J'aimerais déplacer le passage de l'aspirateur au 14 avril de 16h30.
La tâche spécifiée n'est pas programmée, je vous écoute.
Dans ce cas, j'aimerais passer l'aspirateur le 14 avril de 16h30 à 17h.
Vous souhaitez rajouter une nouvelle tâche passer l'aspirateur le 14 avril de 16h30 à 17h.
Oui.
Est-ce bien cela?
Oui, tout à fait.
Entendu. Si vous n'avez plus besoin de rien, dites au revoir.
Au revoir.
Sinon, je vous écoute. Merci et à bientôt.
And the second example is with a user which is really familiar with the system and which is somehow in a hurry. So this is some kind of an extreme test of the system.
Bonjour. Grâce à ce service, vous pourrez interagir avec votre maison en vous exprimant naturellement. Je vous écoute.
Je serai absente le 13 octobre de 9h à 18h.
Le créneau du 13 octobre de 9h à 18h est déjà pris par la tâche ouverture des fenêtres.
Dans ce cas-là, supprimez l'ouverture des fenêtres.
Vous souhaitez supprimer la tâche ouverture des fenêtres? Entendu. Si vous n'avez plus besoin de rien, dites au revoir.
Je serai absente le 13 octobre de 9h à 18h.
Vous souhaitez rajouter une nouvelle tâche mode absence le 13 octobre de 9h à 18h. Est-ce bien cela?
C'est ça.
Entendu. Si vous n'avez plus besoin de rien, merci et à bientôt.
So in this experiment, each user was asked to perform 5 different dialogues, and we randomly sampled, without replacement, a scenario among 10 possible scenarios, and at each time one strategy among the 3 possible strategies, which are the non-incremental, the handcrafted incremental, and the reinforcement learning incremental strategy. We also collected a few KPIs. Some of them are objective and global, like the duration and the task completion. Others are local, like the response delay at each user to system transition, and also the false cut-in rate. The false cut-in rate being the proportion of times where the system shouldn't have interrupted the user. As far as subjective metrics are concerned, we collected the reactivity impact, the human likeness, the efficiency, the global quality, and either the user is willing to or is ready to use this system in his own house. We managed to collect 206 dialogues with 47 volunteer users. Here you have the repartition among the three strategies, and the most interesting result here is that the task completion KPI has been significantly improved by the reinforcement learning strategy compared to the two baselines. As far as the subjective metrics are concerned, they are highly noisy, they have a high variance, so we did not manage to have statistically significant results apart from the reactivity KPI, but we still see that we have a tendency in favor of the data-driven strategy. So when looking at the human-to-machine transitions, here you have their number. So we actually took the mean latency. We measured the mean latency, and what we see in this table is that the reinforcement learning strategy dramatically decreases this latency. And while zooming on the speak decisions only, we see that the reinforcement learning strategy actually, despite the fact that it takes more risk by interrupting the user 4.5 times more than the handcrafted one, it keeps a low false cut-in ratio of 7% compared to the handcrafted one, which is associated with a 30% false cut-in, which is huge. To conclude, I have presented a new turn-taking phenomena taxonomy, a new architecture for incremental dialogue systems, as well as a new environment for simulating incremental dialogue, which supports ASR instability. In the latter, I have implemented a handcrafted turn-taking strategy, and which has been evaluated in simulation. And then I proposed a new reinforcement learning strategy in order to learn optimal turn-taking behaviors, which has been shown in simulation to outperform the handcrafted baseline. And finally, all these results have been evaluated in a real study with the real users. Also, I have identified a few research tracks for future work. So as far as the taxonomy is concerned, it would be interesting to ground it more in a corpus study. Now that we have collected dialogues, the next step is to inject them back in the simulator in order to better calibrate it. And this simulator has been used to learn the reinforcement learning strategies. So now what we can do is try to perform online learning directly with real users. And finally, as I mentioned, we have identified a new exploration problem, which made us bias our exploration between the two possible actions. And this actually raises an interesting theoretical problem, and I have identified a few approaches to try and tackle it, like semi-Markov decision processes and direct policy search. And that's it. Thank you.